Imagine this disk is rotating, okay? And rotating in, let's say, positive direction. That direction is the rotation, okay? Now, this radius is r right here. From here to here is r. And then we reserve the lowercase r for vector functions. So we'll be using radius. Whenever we talk about radius, usually in physics, they use uppercase r, like for that reason, like that. And then theta is this thingy. That's theta. Really, if there's a unit circle, the length 1, and that arc length is really theta now, isn't it? And then we'll call this thingy S. That length of the arc, we'll call it S. Good. And then do you remember this formula? S is equal to R theta. You want me to derive it again, or are we good? That's the arc length formula, right? Okay. Now, what happens if we take a time derivative on both sides? So this is still S, and then this is R. And I'm going to write R first. And then space theta. And then if I differentiate both sides with respect to t, then what do we get? So on the left-hand side, this is some kind of speed of this edge of the wheel moving, isn't it? That's what we call linear velocity. Do you remember 2 years ago, linear velocity, angular velocity packet in pre-calc? Yeah, this is it. And this is R, and we call this omega, not W, omega. So here's the definition of angular velocity. Angular velocity right here, where omega is defined as d theta over dt. How about that? Good. And this is a biggie. Okay. Let's throw a box. Let's box these two things in. So there's that one, and there's this one. Especially this, v is equal to r omega. This was in your packet, linear velocity, angular velocity packet. Good. Then of course, your v is defined this way, right? V is equal to ds dt now, right? Just like dx dt kind of idea. You with me? Now, what happens if you take another derivative on the side? Okay, so here's a v, and here's r omega, right? Actually, I'm going to go back to, hold on, I'm going to go back to the original. So here's S, and then here is theta. What happens if you take a second derivative? So this thing with respect to time. Then guess what the second derivative of the distance thingy is, arc length? That's of course acceleration, isn't it? From our physics, that's known as the linear and this is known as alpha, and alpha is the angular acceleration. Okay, so change the color and let's box that in. This is big deal, the definition. Okay, now so I'm gonna say where, so of course a is the second derivative of s, and then alpha is the second derivative of theta. Okay, now let's think about it. The rotational dynamics. You learned it in pre-calc that one rotation is one rotation, whether you're in the middle of the disk and on a merry-go-round or outside of it. So outside moves faster, but the rotational speed is exactly the same. You know what I'm saying? One revolution is still one revolution. 1 radians per second is still 1 radians per second. It's how much you rotated in a given time. You know what I'm saying? Okay, and here's a huge relationship. Down here, I'm going to write down this thing. S sub t, of course, is S naught plus B naught t plus 1/2 AT squared. Kinematics equation A. Okay, now what is S? Well, S up here is our data now, isn't it? So let's plug in our data. Let's make this thing a little bit bigger. I go really tiny. Okay, so this is equal to our data. So I'm making the transition here. So this is our data as a function of t. Data is varying. Now, there's nothing that's telling you this is rotating at a constant speed, right? It's accelerating as we speak. That's why we have acceleration, angular acceleration. So S is, of course, then R here, theta, original, plus, what was V? V up here is R omega now, isn't it? So plug that in, R omega, then T, good. Well, let's say omega naught, because that's the original linear velocity. And then plus 1/2 A, of course, is all alpha. So all alpha squared. Are you with me? Who's confused? Let me know right now. And then I noticed that there are R on both sides, which are constant. So divide both sides by R. So what we have left is theta as a function of time is equal to theta naught plus omega naught t plus 1/2 alpha t squared. What do we have here? This thing looks like kinematics equation in its own, doesn't it? You know what I'm saying? And that's amazing. That's one of those amazing things about this in physics. So it obeys exactly this angular rotation theta will obey exactly same equations of kinematics. Huh. Questions? So angular momentum. What is an angular momentum, right? See, just like a linear momentum, if something that is in motion wants to remain in motion, right? Let's review what linear momentum was. Linear momentum P is mass times the velocity, okay? So somebody's trying to tackle you. If it's a big guy, then it's going to carry a lot of momentum. But if it's running fast, that also carries a lot of momentum, right? Then what is an angular momentum? Something that is in rotation wants to remain in rotation forever, such as planets, right? And that never stops, both in orbital motion as well as rotation, right? So rotation wants to be preserved. Linear momentum is conserved, right? In physics, something that is in motion wants to remain in motion. You heard that before, right? So something in rotational motion is also preserved. So this is angular momentum, L, and that is defined by R cross product with your linear momentum. So far so good? So then in magnitude, it becomes L is equal to RP. But then our P is MV, isn't it? And then for that we pick up sine theta. You with me? Okay, so if theta is 90, then what happens? So let's say if theta happens to be 90 degrees, then sine theta becomes 1, doesn't it? So our magnitude of angular momentum becomes RMB. So far, so good. Say yes. I'm going to move this thing up there. Okay, now Rm here, what is V in terms of angular velocity? Do you remember this? V is equal to R omega A? Say yes. So what we have is mr square omega. That looks mighty familiar now, doesn't it? Mr square, and this is just a point mass at the moment. That looks like moment of inertia to you, right? If it's a point mass in an orbit rotating. So now what we can conclude here is then angular momentum of the rigid body now. So this is a point mass. I'm gonna, maybe I should put tighter down, right? This is a point mass. Okay, now what about the rigid body then? If you have put all these, let's say rigid body rotating from its center of mass, then your angular momentum will just become I omega now, wouldn't it? You get it? Vectors. And then do you know the direction of the angular velocity? Our right-hand rule, right? That way, that's the direction of that rotational vector. Okay. Seems like everybody's lost. Are you getting this or not? Give me some kind of indication whether this is way out there or not. Now, just like linear momentum is conserved because the planets in orbit, they remain there forever, right? So angular momentum is conserved. So I initial is same as an I same as L final. That is true. So what that tells you is I omega initial vector is equal to I initial omega initial is same as I final omega final. Now, most rigid bodies, of course, don't change its moment of inertia. But as you saw in the video of that dancer, arms out there, these are masses, right? If you bring it inward and rotate, then you're reducing your moment of inertia, correct? Which means, so we have this equality, that whole thing is preserved. So what happens if you reduce this? This gets smaller, then the other one must get bigger in order to have a constant quantity. You know what I'm saying? That's why you can increase angular momentum like this, spin. You with me? So far, so good. Now here's a question. Well, then what happened to the conservation of energy? Because if you increase your angular velocity, you're increasing your kinetic energy. And doesn't that contradict your conservation? I mean, angular momentum might be conserved, but you're increasing kinetic energy. Are you doing any work to increase that kinetic energy? Because in order to increase the mechanical energy, you have to do work, correct? So where is the work? Can somebody answer that question? You really have to do this experiment to see if you sit on the swiveling chair and then have physics like calculus Bible in one hand and physics textbook on the other hand, and if you spin and then bring your arms in, you can actually pick up a lot of angular speed. But why? How are you doing the work in order to give more kinetic energy? That kind of defies logic now, doesn't it?
Does it come from the potential?
There's no potential energy because you're sitting in the same chair, right? Elevation didn't change. There's no spring that you're compressing, or there's no spring that is expanding and giving you the boost. So it's like,
I guess it's the work of bringing the books in.
Yeah, if it's a heavy book or dumbbell and you have done this, it's not easy to bring your arms in. If it's just your arm, it's not that hard, so you don't notice it. But if you have a heavy dumbbell weight on your hands and then you rotate and you bring that in, you can pick up a lot of angular velocity. but it ain't as easy as you think. It's just like, can you imagine like heavy objects in both of your hand and you're rotating and you have to bring it inward? It's not easy. That's the work. So you are doing the work in order to gain kinetic energy. You get it? Okay, then I'd like to give you something called the impulse equation. Are you in a momentum section in your physics class yet? No? Yes? No? Okay. You learned this in your physics class. So, see, P is equal to mv, right? What happens then if that velocity changes? You know what I'm saying? So if that velocity changes here from this, let's look at it. Do you see that dp, and let's keep it as a magnitude, is equal to m dp over dt, let's just say it this way. dp over dt is, of course, m dv over dt, right? But tell me what dv over dt is.
Acceleration.
That's acceleration now, isn't it? Right? Oh, okay. So we don't have to really write it like that. This is ma, right? That's a force. Wait, derivative of momentum is a force. So far with me? Okay. Now I'm going to, you must be familiar with this now. Force, right? dt. So far so good? And what happens if I integrate both sides? From A to B and from A to B. Then time is equal to A to B. And then right-hand side still remains same thing, right? F as a function of t, dt is what that means from A to B. And guess what we pick up on the left-hand side? Do you believe it? Because it becomes P and then initial minus final. You get it? This is known as the impulse equation in physics. Many times if the force is constant, then it's just force times delta T. But it really means when in your physics book, when you say you divide, that really means derivative most of the time. And when you say you multiply, it usually means integral. Okay, so let's say you are catching a ball, right? You're sitting in a fence behind the home run fence, and then there's a ball coming at you with a lot of velocity, and that baseball is pretty hard. When you catch it, do you put your hands forward as you catch it, or you back up a little bit? Which one hurts less? Anybody who caught a pretty dense ball, you know the answer to this. You want to back up to catch it, right? Because that ball has an initial momentum, and then you want to bring it down to 0. So this is a fixed quantity, right? So if you take longer period of time to catch it, then you don't have to exert as much force. You know what I'm saying? So this is constant, which means it hurts less in your hand. This is known as impulse equation, which is pretty important. You will see it someday. Okay? Now I'm going to do the similar thing with the angular momentum here. Okay? So from up there, L, angular momentum, is equal to I omega, right? Actually, I'm going to keep it as just a magnitude. So if you have a vector equation here, that can get really crazy here. So why don't I take a derivative here? So dl over dt as I being constant. What's the omega dt? What's the derivative of omega?
Alpha.
Alpha, angular acceleration, right? So derivative, wait, I alpha. What was I alpha before? What is I alpha?
Torque.
That's your torque. So dl is equal to your torque times the t now, isn't it? Isn't it? Now we are going to integrate both sides. So if we integrate from a to b, meaning time a, time b, then this side, it becomes delta L, which is change in angular momentum. And the other side, it becomes this thing, it's still integral equation. And this is equivalent impulse equation in angular momentum. So whenever you want to calculate the change of the angular momentum, you integrate whatever the expression of the torque.